Okay, good afternoon, everyone. We're going to begin the webinar. I'd like to start off by welcoming everybody to Personal Energy Absorbers and Lanyards, how changes to CSA Standard Z259.11 affect Canadian workers. My name is Ramsey Cardozo, and I work in the Marketing Communications Department within Personal Safety. I'm thrilled to be the moderator today and welcome all of you from across Canada. Don Medeiros and Nicola Skinner will be our presenters today. Don will take us through about 20 minutes of technical information about the CSA standard change, and Nicola will discuss operational changes 3M will support you on during this change. Nicola Skinner is the marketing leader for the fall protection business for 3M Canada. Nicola has been with 3M for 8 years, and during that time has been part of different business groups with various roles and responsibilities, including business services, key account management, and marketing. Each of these roles has required a customer-first mindset. Nicola enjoys collaborating with 3M's technical team and fall specialists to provide our customers with the solutions they need to get their jobs done and home safely at the end of the day. Don Medeiros is our Senior Safety Application Professional for Fall Protection Solutions at our Fall Protection plant in Mississauga. Don brings to 3M Canada a Bachelor of Applied Science from the School of Occupational and Public Health at Ryerson University, as well as 17 years of practical experience in the field of occupational health and safety. He has worked predominantly within the construction sector in a wide range of industrial and commercial settings and has been practicing Canadian Registered Safety Professional for over a decade. In recent years, Don has shifted his safety focus to fall protection, given the continued frequency of fall injuries and fatalities, both in construction at a large through training, disseminating technical specifications, and field consultation for various applications. Don has been a certified instructor in Ontario under the Ministry of Labour Working at Heights program with both the Infrastructure Health and Safety Association and 3M's Fall Protection Group. With that, I'd like to hand things over to Don.
Thank you, Ramsey. Good afternoon, everyone. Thank you for joining us this afternoon. If you're anything like me, you're busier these days than you were previously. So I appreciate you taking the time out and discussing the safety topic today. Just bear with me as I try to get this slide to go. There we go. So I won't repeat my intro. Thank you so much, Ramsey, again. Basically, that's what she had just dictated. And all I want to tell you is that I'm a health and safety advocate. I have been for years, partly because of my time in the field, work that I've done, and people I've worked alongside, including some family ties. So I take this very seriously, and it's a very important part of my life. I've gotten into fall protection because although we're in a developed nation, great part of the world to work in, safety is still very much an important issue for us because at any given time, people are not protected to the level that they need to be, especially with regards to fall protection. So that's enough about me. So our topic today, of course, is the CSA standard change for personal energy absorbers and lanyards. This is our agenda, and you'll notice right off the bat that there is quite a bit under the energy absorber portion. Of course, both go hand in hand, and that's the discussion, but the changes reflected in the standards are heavily under the energy absorber portion. So we're going to talk about all these aspects that you see in front of you there. So personal energy absorbers, what's changed? So the previous energy absorber classifications under the last version of the CSA standard, the energy absorber classifications that we've all become accustomed to were E4 and E6. So E4 being the standard category, 4 kilonewtons, 4 being represented by kilonewtons, and E6, the heavyweight category, or 6 kilonewton force. These have been removed in the new standard, so they no longer exist in this new standard. These previous CSA classifications basically amounted to 2 worker mass ranges, 2 maximum arrest forces, and 2 maximum deployment lengths for energy absorbers, as you can see in that chart below. Okay, so we're going to talk about these both E4 and E6 and how they've transitioned with regards to each category here. We're going to talk about worker mass range first, and then move along to arrest force and deployment. But as you can see there, pretty simple. There was 2 weight or mass categories that people understood for the users. You know, if I'm 150 pounds, pretty straightforward what worker mass range I fell into and what would be in turn my maximum arrest force and maximum deployment. We're going to try to keep this topic as simple as possible, but the change offers some really neat advantages that we'll discuss. But first, worker mass ranges. So worker mass ranges, under the new standard, CSA no longer dictates what worker mass ranges are permitted. So this freedom is now given to the manufacturers. All right, so 3M, as a manufacturer of fall protection, we have a new range of various ranges due to the type of equipment that we have and that we have designed, and obviously our competitors that are certifying to this standard are following suit. So you're going to find that there is quite a bit of change here. So based on the 2 types of personal energy absorbers we manufacture, and you can see that below, 4 total worker mass ranges are permitted by us, by 3M. So as you can see, 2 sets of ranges for each type of energy absorber. So the energy absorber type listed on the left, we have shock pack and tubular web. And let me explain what those mean. So by shock pack, we mean a traditional energy absorber pouch. Okay, you might be familiar with the ones that are web that are folded onto each other in a specific stitch pattern, and it's, you know, often covered in either a clear plastic pouch or some sort of other material. Tubular web is basically elastic webbing. Okay, so where you see an energy absorber not necessarily in pouch form, but it is partially oriented yarn and elasticized web. So the energy absorber is throughout the length of the lanyard and looks like you know, a bungee in essence. So those are the 2 types of designs that we have, and according to that and according to the new requirements, we have created these mass ranges. And as we look further on, there'll be a graphic to represent this better, so we can do a comparison. But basically, you can see for the traditional shock pack style or a smaller pouch style, we have anywhere from 121 pounds at the start in the first mass range. And moving over to the right, it goes up to 420 pounds. And you'll note, obviously, that there's some overlap there. So there are users in weight categories that might consider one or the other. And as for the tubular web or elasticized web or partially oriented yarn, in this category, you can see the mass range is different. There's overlap as well, but it's a little bit less ground covered here. So you start at 132 pounds and up to 385 pounds allowed by the design parameters and the parameters of the new standard. Okay, so that's worker mass ranges. That's how it looks right now for 3M. Here's the graphic I had just mentioned. So looking at that graph, you can see you have pounds on the left and then the different categories on the right. And this is comparing the old comparing the old standard to the current standard. So E4 and E6 is shown there. You can see there was initially overlap with that arrangement as well, starting at 100 pounds up to 386 pounds from the standard to the heavyweight category with overlap. And now you can see with the ranges that I just described in the previous slide for 3M, Shock Pack 1, Shock Pack 2, Tube 1, and Tube 2, you can see this is very similar, okay? But you can see that our range for our current design and this phase of launch of lanyards that we currently have, it starts at 121 pounds, which serves most of the population if we start there, but obviously doesn't cover every single person, but probably 99% of the population. And you can see that we've been able to increase the weight range as is permitted by CSA. It's up to us to select that range, obviously, and you can see it goes up to 420 pounds under Pack 2. Okay, so and again, important to note, this reflects a user's mass with all their clothing, PPE, any tools that they're carrying. That is your total weight. That's how you have to consider these numbers. And information regarding this sort of thing is covered well on our website. Going through some of the line items that you see on the right, as you may have been reading as I was going through that graph, the last three bullet points are the most important to take away from this. So I'm going to start with the third bullet point. This allows for Factor 2 falls and the approval of the lanyards under the standard. So for those that aren't familiar, Factor 2 falls are falls with essentially tying off at your feet. Okay, so a traditional lanyard used in a fall arrest scenario, not a restraint scenario, but a fall arrest scenario, it is commonly required that the user tie off to an anchor point above their head or as high up as possible. We have manufactured for years Factor 2 type energy absorbers that allow you to tie off at the foot level. But you can appreciate with a standard 6-foot lanyard, that means if you're tying off at your feet, you have potentially brought your potential free fall to 12 feet, okay, accounting for the lanyard's length at your working position, and then that lanyard down over the edge for where you have fallen. So anyways, this is talking about Factor 2 falls. Our weight ranges, consider that, and previously with E4 and E6, there was nothing to address this. So now this allows for this within the parameters of the standard requirements. The next point, allows short clearance calculation where required. So although E4 and E6 were convenient categories, easy for everyone to understand, and for selection of lanyards and energy absorbers, the clearance available really painted people in a corner, so to speak. So this will become clear in the next few slides. But what this new the standard allows is for shorter clearances in cases where a lot of job sites, places of employment are going to more stricter requirements for threshold height for a personal tie-off. I know a lot of places have 6 feet requirements or 4 feet requirements. So this is becoming harder and harder to meet. And of course, we don't want anyone to bottom out. Okay, the whole purpose of this is to keep people from falling and hitting the ground or hitting obstacles on the way down. Finally, the last point here, this allows for longer free falls and heavier users under the standard. So I already had mentioned, the heavier users, this allows us to go beyond 386 under this standard, and allows us the freedom in terms of our design and our testing to make equipment that not only will help us with clearance, but will help us limit the amount of free fall if needed as well. Okay, so maximum arrest force and maximum deployment. Let's dive into these terms a little bit more. So under the new standard, CSA is no longer interested in setting individual parameters for maximum arrest force, as we saw with that initial chart. We know what those were, 4 kilonewtons and 6 kilonewtons. The new overall maximum arrest force for all personal energy absorbers, as determined by CSA, is now set to 8 kilonewtons. So basically, they set a general ceiling for the maximum arrest force, okay, and left it to the manufacturers to design and test everything to fall under that. Okay, so that allows a bit of freedom. Maximum deployment had been set by CSA at 3.9 feet and 5.7 feet. Okay, so the maximum deployment is, we're talking about the maximum length of energy absorber that deploys once your fall starts to be slowed down. Okay, so we have some slides on this later, but very briefly, once you start to fall, you're accelerating, and then once you have the lanyard taut and the energy absorber beginning to deploy, that is your added distance at this point that you are considering. So if you had a traditional 6-foot length lanyard, you'd be adding 3.9 feet to that if it was E4, or you'd be adding 5.7 feet to that if it was E6. Okay. Now the manufacturer dictates maximum free fall distance. So we dictate that as a manufacturer, and in turn, the maximum deployment permitted. Okay, so free fall distance and maximum deployment go hand in hand. Next, the new maximum deployment lengths as determined by 3M, okay, for our products, not anyone else, our products, in the 4 different worker mass ranges that have been discussed so far, are 2.37 feet, 2.96, 3.29, and 3.48 feet for our DBI Sala brand, for example. So we have 2 major brands under 3M, DBI Sala and Protecta. We're talking specifically about DBI here. And you'll notice that these deployment lengths are quite a bit reduced from the E4, E6. Instead of 3.9 feet or 5.7 feet, you can see that you've basically done a lot here to minimize the clearance needed, okay? So CSA is now putting greater emphasis on deceleration and limiting free fall distance. So this is the reason for the move. As more complexity comes in, keep in mind the idea is freedom for design for manufacturers and being able to limit deceleration forces and free fall distance for the end user in the fall event. So these are pretty important and allow for fine tuning, if you will. Maximum arrest force versus deceleration. So maximum arrest force is the peak force exerted on a worker or test mass during a fall arrest. Okay, that's right from CSA. So that is the ultimate force exerted on a worker. Deceleration, as some may be familiar with this term, is the rate at which an object or mass slows down. Okay, 9.8 meters per second squared is how that is described mathematically. It is also expressed as a force, the equivalent of 1 G. And note, we're talking about G forces here, not grams. So my brain, every time I see that lowercase g next to a number, I think grams, just not to confuse the matter. We're not talking about weight here. We're talking about G forces, okay? So that is the unit that CSA has chosen to go to talk about deceleration, okay? And deceleration is basically the opposite of what most people are familiar with, acceleration, which is, of course, increasing your rate of speed. This is talking about slowing objects or masses down. Okay, we're talking about, remember, we're talking about falling force, which initially you're accelerating, but in terms of energy absorbers in the context of this conversation, we're talking about slowing the body down as safely as possible, okay, to limit the amount of forces on the body. So finally, the focus now is on what forces workers experience over time when a fall is being arrested. The goal? Exposure to a tolerable force load for a very, very short time. This will help ensure that users of different masses will experience similar deceleration, helping to ensure a consistently lower exposure to peak forces over a shorter time. So in other words, if you weigh 125 pounds or you weigh 375 pounds, anywhere in that spectrum, in those mass ranges we discussed, you should be experiencing a similar type of fall, and it doesn't matter where you sit in that spectrum, so long as you're using everything as per the manufacturer's instructions. You should be experiencing these similarly and hopefully not experiencing an injury during a fall. All right, so I thought it would be helpful to talk about deceleration in terms of what CSA has set up in terms of real world examples, because not everybody is used to talking about this sort of stuff in terms of G-forces. For years and years, we've been talking about kilonewtons and pound force when we talk about stuff like fall forces, okay? But we have this move to G-forces to better describe deceleration. So these 3 bullet points you see at the top with the numbers, these are the parameters set up under CSA for testing. So maximum deceleration, the ceiling, okay, is 10 G-forces, okay? Deceleration is to be between 8 and 10 G-forces for up to 0.1 seconds. So very brief amount of time. Anybody who's taken a fall, whether on purpose or by accident, you know how quickly you accelerate. And we're going to talk about that in the next few slides. So we are really talking about a small moment in time. And we have maximum deceleration, a deceleration range over time, and then average deceleration. Okay, so that is to be greater or equal to 2.3 Gs and up to or equal to 7 Gs. Okay, so the standard goes deep into this, and we don't have to for the purposes of the scope of this presentation. What I want everybody to understand is what these G-forces mean in terms of real life. Okay, so let's look at some examples on the left. Okay, so G-force, gauging it, definition from Canadian Oxford is the force of acceleration due to gravity. Okay, so you know, we have a scale basically rising from top to bottom. We have a shuttle launch, an F-16 fighter jet. People are used to hearing about G-forces when we talk about aviation, okay? So there's numbers out there for various things, or for, you know, fighter pilots and the like, okay? But now let's look at roller coaster plunge. Many people have experienced something like that. As the numbers rise, just take notice, okay? So we're at 4 to 6 G-forces for a given plunge in a roller coaster. So after the roller coaster crests and begins to fall, that is the force somebody would essentially feel or be subjected to. Car crash at 64 kilometers an hour. It's a bit of an odd number. I think it was initially miles per hour. It's just been converted for us. That is a 35 G force, quite substantial. And then as you move down, you see a heavyweight boxer punch, a football hit, or a concussion, and we have various ranges. But you're getting the idea here that, you know, as the higher you go, the more dangerous it is to you. And if we look back at on the left side of the bullet points and these ranges of numbers, basically see anything over 10 Gs can be pretty dangerous for you. Okay, so as a maximum. Okay, so again, looking at the examples on the right, the real world examples, I put the question out there. So which example describes a deceleration force? All right, so a lot of these are describing acceleration, if you'll notice. But an easy one to pick out here, the car crash. Okay, so we're talking about 35 Gs would be experienced by a person in that car from an abrupt stop by the car going 64 kilometers and then quickly having to stop because it collided with something. So that is what we're talking about, deceleration, slowing a body down. So at first you accelerate due to the fall, but as soon as your energy absorber is going into action and beginning to deploy, we're talking about deceleration. And finally, it says which examples are associated with injury. Okay, as it's probably evident to you out there that you know, the examples at the bottom as we increase the forces over 10 Gs, this is becoming more and more a danger to the human body, and you're likely to experience injury, if not a fatality. So very serious, and we can see what the body can typically tolerate is the first few examples above, but even then, not everybody is the same, and we have to take that into account as well. Okay, so as I alluded to previously, for those of you out there that have experienced the fall and hopefully not been injured, you know what it's like to have that feeling in your gut, so to speak, when you begin to fall, and it happens very quickly. And a lot of people don't appreciate this, and call it worker experience leading to complacency, overconfidence, what have you. But sometimes people think, oh, if I start to fall, I'll grab something, I'll catch myself. You really do not have time to act once you start to take a fall. What I want to talk about here in these next two slides is something for everybody to think about. So this is taken from one of our 3M Fall Protection Group courses, a course that I've given. And just to gauge people's ideas or preconceptions of how they think people experience falls. Okay, so the question asks, based on your impressions, approximately how far and how fast do you think you would free fall in 2 seconds? Okay, so remember I said 0.1 second, that's a very short amount of time. 2 seconds feels like an eternity when you fall. I can tell you, for somebody being, in my lesser days of sanity, I've purposefully jumped out of a plane. Probably won't do that again. But I know just how quickly this happens. So I'll let you think about that for a moment. Again, think about the distance. How far would you reach in 2 seconds? And how fast? How fast would you go? What will your speed be at 2 seconds? Okay, so think about that for a moment. And now I'm going to give you the actual answer. So if you picked the most extreme for both options, distance and speed, you are correct. A lot of people don't reach this conclusion. So hopefully this is enlightening either way you went. But let's look at the two lines on the graph very quickly. So the bottom axis has your time, so 0 to 5 seconds, as you can see there. And remember, the question asked how fast and how far do you travel in 2 seconds? So looking at the 2 second mark, if we look at the red line, that's the distance you travel, okay? And you can see 20 meters at that mark. And then if you're to continue falling freely in the air, at the 5 second mark, you'd reach up to 123 meters. Quite astounding. And with your speed, this surprised me the most at the first time I learned about this. 70 kilometers an hour in 2 seconds. So free falling again, no obstacles. You reach in 2 seconds approximately 70 kilometers an hour. At the 5 second point, you're at 175, which sounds ridiculous, but that you're in that neighborhood for sure. And I don't know, I haven't done the math, but at some point you reach terminal velocity, and that's for skydivers, not for this discussion. Okay, so I hope that gives people an idea just how quickly you start to putting yourself in harm's way the longer you fall. Okay, so that's why we talk about deceleration, minimizing your length of free fall if possible, and limiting forces on the body. All right, so free fall distance. This is pretty simple. Under the new standard, CSA no longer stipulates a maximum free fall distance, okay? So you can see in the graph below, the chart, I should say, the previous was 5.9 feet, okay, or roughly 6 feet, if you round up. The current standard, this is what it says: the maximum free fall distance shall be specified by manufacturer, and it would result in 0.7 to 0.95 of the maximum deployment. Okay, so that's a bit of a safety buffer. Okay, For 3M, we've kept this part simple. It remains 5.9 feet as with the previous standard. So if you look at the picture on the right, the acronyms there I'll help with. Basically, your L is your lanyard or length of lanyard, okay? And it's showing you initially the user at a platform tied off overhead, but forward. And basically, it's denoting the height of D-ring, okay, and the free fall distance based upon where that worker is situated with regard to their anchor, okay? So this is showing you, after the person takes a fall, that's just the free fall, okay? So this is not showing you the total fall, which would have an energy absorber, and that person would continue to go a little bit further down, okay? We have a better image to talk about that. Okay, so important, the free fall distance hasn't changed in terms of 3M, so that's our set point, if you will. Okay, calculating fall clearance. This has been something that has always been done. I shouldn't say it always, but for quite some time, this has been done. This is a graphic from the standard to help us sort of understand and visualize. Not much will change with this, okay? As a result of the new standard, users will have access to more precise info for energy absorber deployment length to be provided in manufacturer instructions. Instead of plugging into the equation, either 3.9 feet or 5.7 feet into the following equation, the user obtains this number from the manufacturer's own labeling and instructions. Okay, so if I can very briefly cover this, we can get, talk about, there's courses dedicated to this that you can go quite in depth, but for the purposes of this presentation, we're going to keep it simple. This is a great example visually because it's showing you somebody connected in a personal fall arrest system with a horizontal lifeline right at the top, okay? So you see that based on the design of those systems, you're always going to get deflection, okay? So you have to account for that, the maximum system deflection, okay? So that's the first item at the top right. As we move down, you see we're accounting for the lanyard length, okay? So 6 feet is common, but there are many different lanyard lengths out there. And then what we've highlighted here is XPEA, the personal energy absorber deployment. So the length of that energy absorber as it's slowing you down from that fall experience. And then after that, we have harness stretch. Okay, so in every case, if you fit the harness perfectly, great, but you will still have it stretch, and you have to account for that. And there's guidance in our manufacturer's instructions about how much you should put for a number there. And 1.5 meters or 5 feet, initial D-ring to toes, so the height of D-ring. And finally, a safety factor. Okay, so we have 2 feet. That's typical for one of these calculations. So, adding all those up is typically how you reach your appropriate fall clearance. So the key, what we're stressing here, is that highlighted portion where people would normally put 3.9 feet or 4 feet rounding up, or 5.7 feet rounded up to 6 feet. Instead of using those E4, E6 numbers, those are no longer relevant. So you really have to pay attention to the manufacturer's labeling and instructions for what number you would put there. Okay, if you need to be precise for a low clearance, a short clearance situation, you can be more precise. If you want to use maximums, you can use maximums. But you got to be very careful, especially in a limited clearance scenario. Okay, so we talk about this on this slide here. So should the need arise to calculate a fall clearance for low clearance applications, okay, so where you're very limited, you're very close to ground, and you don't want to hit ground, it says here, confine those calculations to a competent person or a qualified person, okay, so somebody with the knowledge, training, and experience to safely execute the work, or even by qualified person, we would mean somebody perhaps with an engineering degree with experience with fall protection systems. Make the results of that calculation part of a fall protection plan for that site. Very important. So something like this shouldn't be, for minimal clearance situations, you have to get it right. You cannot fail once. You want to be sure of your numbers. You should really put this in a written plan. Remember to limit users to weight capacity selected in the plan, obviously. Remember to complete all variables accurately. That's, of course, key. It is basically incumbent for the competent person or qualified person to know these three things: user weight, free fall distance, and deployment distance. Okay, those are your key variables that you just got to know, and you got to be sound with how you plug these into your equations. Okay, people's lives are literally on the line, right? Okay, moving on. So it's not always as complicated as a horizontal lifeline system, taking into account deflection of the anchor, et cetera, et cetera. So what we've done with our instructions and labeling, which our competitors have to do similar, you're going to find charts that look like this in the instruction manuals, okay? And these are very, very helpful. I'm going to walk you through how you basically read one of these, okay? So we have two examples. If you look at the top of both charts or graphs, we have shockwave in the weight category of 80 kilograms to 175 kilograms. All right, shockwave is one of our products, okay? And then on the second graph, you have shockwave 176 pounds to 385 pounds, okay? So the upper category or mass range. All right, so because we're just displaying the second graph in pounds and feet, which is what I'm comfortable using, we're going to use this example, okay? So as I talk about the items on the left, follow me with the graph on the far right, okay? Shockwave 176 to 385. So look up the worker weight on the vertical axis. So for simplicity of this exercise, and so everybody can see it as clearly as possible, I'm going to pick something simple. So I'm going to take, for example, let's say I'm 235 pounds with all my PPE on, my work boots, everything, 235 pounds. So I find that on the vertical or y-axis, okay? And then I run my finger across to the right. It says where the worker weight falls between grid lines, use the next grid line. So all that's saying is if I was somewhere between 235 or 245 pounds, you go to the next grid line. So if I was 240 pounds, I would use the 245 pound line, okay? So back to it, as I stated, for this example, we're gonna say I'm 235 pounds total with all my equipment. I move my finger to the right until it intersects the line on the graph, okay, the diagonal line, okay? And that lines up perfectly for this easy example at 1.5 feet. Once you meet that diagonal line, you bring your finger down, and the number down below is your energy absorber deployment, okay? So as it states there, where the worker weight and graph line intersect, determine energy absorber deployment, XPEA, from the horizontal axis directly below the point of intersection. So in this case, 235 pound worker based on a 5.9 foot free fall. Again, remember that's our standard determinant. It is different for our factor 2 lanyards and energy absorbers. And I have a note on that towards the end of this section. So 235 pound worker, 1.5 feet is my energy absorber deployment. So that means if I had a 6-foot lanyard, I should be considering that will become 7.5 feet total, 6 plus 1.5, once that is deployed, okay, in a fall arrest event. So I hope that helps. I hope that makes sense. Now just instructions and labeling here. This is right from the CSA standard as well, and basically showing you how the labels will appear under this new standard. And you have just black font on white background in one scenario, and the opposite, white font on black background in the other scenario. And This is based on your free fall equaling 6 feet or under. It's going to be a white label with black font. And if you have free falls greater than 6 feet, then it's going to be white font on black background. Okay, so this is just for users to quickly pick out if they have a special lanyard or a factor 2 type lanyard. Okay, again, this is scenarios where you don't have an anchor point above your head that's convenient, and you can only tie off at your feet. Say for an iron worker climbing and walking on structural steel. Okay, a lot of scenarios, that's all you can do. So if we look a little bit closer at the label, let's look at the left one. We see maximum free fall distance in the first quadrant. That's 6 feet, right? We have our weight range, including tools, so 130 to 310 pounds. Maximum deployment, okay, and this is again CSA's example, not ours with our numbers. It just for this it says 4.6 feet, okay, maximum deployment, and then a deployment factor, okay. This isn't crucial for those in the field necessarily, but for those that get deeper into the deployment factor or P factor, there is more detail in the standard about that, and it's not covered in the scope of this presentation. But there is training that can be given beyond this, of course. Okay, so that's going to be on the labels. Those key 3 numbers we talked about already, those first 3 quadrants. Flip it over to the right side, 12 foot instead now, maximum free fall distance. We're talking about the same weight category. I want you to note the maximum deployment, just for argument's sake here. So 4.6 feet in that first label. Look at it now, 9.2 feet. So, that is a big difference, and people might wonder, well, why is it so much? That's accounting for how much your free fall that person is experiencing, and how you got to slow that body down to experience similar fall forces. Okay, so to slow that person down, you need a lot more clearance. Okay. Okay, so that is energy absorbers. There's only a few slides on lanyards. There hasn't been too many changes on lanyards, so this should go pretty quickly, and then we will be into our Q&A portion. Okay, so firstly, there is a new classification, okay, Class Y, where there was previously just A, B, C, D, E, F. The weird Y comes about because of just the nature of the lanyard itself. Okay, it's a Y lanyard. It was referred to in previous version of the standard, but now it's formally classified. Okay, and it's Y because it's easy to remember. Dual leg lanyard kind of looks like a Y, and that is why it is that. The key out of this slide really is the last point. The new design requirement that a Y lanyard shall contain, not should, shall contain at least one energy absorber. So reason for this being, at least my understanding, you have a dual leg lanyard. The intent of that design is so somebody can transfer their anchorage point and not be subjected to a fall hazard, right? So in that sort of scenario, you cannot be in restraint. Okay, typically somebody is going to be in a climbing mode. They might be putting together scaffold, or if they're mobile, they're probably not in restraint. So you really should have an energy absorber, because as we know from our discussions thus far, fall forces are very unforgiving. And if you're using a lanyard in a fall arrest scenario, it really should have an energy absorber. Okay, it's great if it keeps you from falling and hitting the ground, but you can sustain some pretty serious injuries with some of the forces we've been talking about, even if the harness and lanyard and the anchor hold you all together. Design requirement changes, classes A, B, C, and D. So firstly, class A, B, and C lanyards, that's rope, web, and wire rope construction. Modified design requirements to allow the lanyard to have class 1 connectors or integral terminations that may be connected to other fall arrest system. Okay, so that is important on its own. Talking about integrated terminations, We're just going to leave it at that, just so that you're aware. Again, we can go deeper for another session. Class C wire rope lanyards. So they added a new requirement that the wire rope lanyard shall have an integral energy absorber. So as per my recent comments about the Y lanyard and how falls can be very unforgiving, and you should have an energy absorber if you're in a fall arrest mode or application. Wire rope is the least forgiving of any of these material constructions. So that's why they just went ahead and said you shall have an integrated energy absorber on such a lanyard. Further, construction of the lanyard eyes, okay, formed by a back bend eye with a swage construction was removed. So now it specifically mentions Flemish eye splices secured with mechanical sleeves. So it's just in how they terminate the cable, at the end of the cable, as you can see in that faded picture on this slide in the background, there's a loop typically, and then there's some sort of mechanical way to neatly tidy the end of that wire rope, because it's just not too different from regular rope. Wire rope has to be terminated in some fashion, and it is basically saying a Flemish eye splice secured with mechanical sleeve is now required. Okay, so there's different ways to do it, and this is particularly important in the province of Alberta, where this appears in the legislation, but it's just good practice. So now it's right into the CSA standard. And finally, covers on mechanical sleeves, okay? So where the ferrules have been swaged on, for inspection purposes, these shall be clear in color, okay? So again, an improvement to allow ease of inspection to make sure, the end termination of the cable hasn't gone awry. Finally, Class C lineman's pole strap, they just removed working position lanyard from the title. And finally, note, no design changes to Class E or Class F, the other lanyard classes, okay? So those remain unchanged. And finally, labeling regarding classes A and B, okay? So you notice these two lanyards we have on the right, there's a rope version and a web lanyard. There is no energy absorber, as you can see. Okay, and as we've been talking about in the last few slides, if you're going to take a fall, you really, really want an energy absorber to protect your body. Okay, so what we're saying here is the new requirement for all Class A and Class B lanyards. So again, the type that you see to your right, that do not have integral energy absorbers, they're still allowed. Okay, but these are intended for restraint applications. Okay, so what we mean by restraint, we are meaning keeping that individual not being able to let them fall, essentially. Okay, so there is no fall arrest to be had. They are in a restraint mode. Okay, sort of like a dog on a leash. The following warning shall be included in the markings. Okay, so warning for fall arrest, an energy absorber is recommended to be used with this lanyard. So manufacturers may allow for an energy absorber to be added, but really have to follow manufacturer's instructions, and best to use a lanyard already with an energy absorber integrated into it. So that's it for lanyards, and that is it for my discussion. Thank you for joining us again this afternoon, and I will hand it off to Ramsey.
Awesome. Thank you so much, Don. Thank you for all of that information. We do have a couple of questions that have come in. So the first question is, how would you suggest an end user manage these new guidelines on site? E4 and E6 seemed easier.
That's a great question. Thank you. So yes, it was easier, but as I've discussed, the new standard does allow for such things as shorter clearance requirements and keeping people from bottoming out, allowing for heavier users, et cetera, et cetera. So for those in jurisdictions where this new standard change isn't in law, not too much might change except when you start to buy a newer product. So all the manufacturers certifying to CSA obviously move to the latest standard to certify to the best and most current, and you will start to get a mix in your inventory of traditional E4 and E6 lanyards and the new stuff. So for those in other jurisdictions where you go to the latest CSA standard, that's how it's written in law, it's easier to manage the inventory because you basically have to change out everything. But for the most part, Canada-wide, it's not that case. So basically, if safety managers, operations managers, the employer really has to do their best to manage the inventory. And in terms of training, whether internal or external, we really have to pay attention to workers at the outset, just knowing how to select the lanyard by their mass and following the user's instructions. Okay, so it's very, very important that they look at those user instructions. You get a lanyard, buy it new, great. It's in a plastic bag usually. People like to throw out the manual at times because they think they know how a lanyard works. It's, it seems straightforward, but really now more than ever, really pay attention to those instructions and follow them closely.
Okay, great. Thanks, Don. Our second question is, how can I learn how to do the clearance calculation using the P factor?
So this is a great question, and as I alluded to in the presentation, this is not in the scope of this presentation. It is not for everyone. I'll say that right now. It's for people deeply into fall protection engineering and high-level fall protection planning. We are actually looking at a course development for this in concert with our friends in Fall Protection Group. But this is still in its infancy, but it is helpful for those that are that much involved in it and want to know more. Yeah, we can definitely teach more about the P factor. And I'm happy to talk about this with anyone beyond today's presentation. I understand from Ramsey, and she'll talk about this, that there'll be a way to connect with us beyond today's presentation.
Great. So our next question is, why do all wire rope lanyards have to be equipped with an energy absorber?
So I believe I spoke to this briefly. It basically amounts to that wire rope cable is very unforgiving to the body. It's great if you're a welder and minimizing your exposure of web being burned through or something like that. It has its benefits, but one thing that is no good for it's stopping a human body from falling. So that's why an energy absorber is critical to minimize the forces. If you just compare a wire rope or cable lanyard to a regular web lanyard, the web lanyard stretches a lot better and will provide a little bit more relief. So basically that's the reason why wire rope is unforgiving.
Great. So our last question is, what do I do with old inventory? Is it okay to sell inventory under the old standard?
Don, I can answer this question, similar to how you alluded to your first response in terms of it varying by jurisdiction. But in general, any product in inventory or being used on a work site that was manufactured before the date of February 1st of 2020 can continue to be sold and used, again, in most Canadian jurisdictions. The key message here is to check with your local legislation to ensure that you're compliant. But again, in general terms, lanyards manufactured after the date of February 1st, 2020 have maintained their same part numbers, but descriptions have been updated to reflect the new weight classes that Don's described in this presentation today.
Thank you so much, Nicola. That was actually our last question. So I'd like to thank you both again. I really appreciate your time today. And for everybody on the call this afternoon, feel free to contact your 3M Key Account Manager if you have any questions about this topic. The presentation from today will be sent to you via email, and I hope you all have a wonderful day and a great weekend. Thank you so much.